Hello, this is ET350 Lecture 6. What we're going to cover today is a look back at the torque speed curve for a DC motor. And we talked about some of this stuff for during the last lecture, but we're going to revisit it and make sure we just really hit it home how all these variables affect the torque speed curve. We'll look at the equation for the stall torque and the no load speed. And with that, we're going to look at the power speed curve for a separately excited DC motor. Now, all this is separately excited. Then we're going to switch gears a little bit and then talk about a series DC motor. And in a series DC motor, the field current is now created by the same voltage source as the source for the armature, and it'll be run in series. And what the biggest thing is going to happen is that the flux is created by IA. And so notice in your Bill's law, the Lorentz force equation, your back EMF equation, there's no more phi in here. It's dependent on IA from Ampere's law. Then this is your nodal Ohm's law. So these are kind of the three summary equations for the series motor. We'll go over that. With that, we'll look at the torque speed curve for a series motor and contrast it and compare it to what we have for a separately excited. Look at some properties, and then we'll see why a series motor is also called a universal motor. All right, so let's go back to the equation we derived for a separately excited motor. We got this equation: torque developed equals negative k phi squared over Ra omega m plus k phi over Ra Vs. Okay, and if you forgot what this looks like, it's a y equals mx plus b scenario where you have omega m and you have torque developed and you're going to have this negative slope. This is your no load speed. This is your stall torque. All right. So I want you to think of this curve as your ability for the motor to create torque, right? At the higher speeds, your ability for the motor to create torque falls off because the back EMF that's dependent on speed goes up. At a low speed, there's no back EMF or very little back EMF, so you can pull out a current. And by Bill's law, you can get a lot of torque with a lot of current. In this situation, you have a motor state, and over here you have a generator state. And in this generator state here, notice the torque is negative and the motor is being pulled by the external environment faster than it wants to go. And you reverse the torque, which means you're going to reverse the current and you're going to get an energy charge on your voltage supply. Okay. Now, the stall torque is this guy, and it's governed by the situation when omega m is 0. And it's pretty easy to see if this term goes to 0, the stall torque is just this guy, k phi over Ra times Vs. So this is k phi over Ra times Vs. Okay. Now, let's say we're at the situation where we want to, well, what happens when the torque is 0? Over here at the no load speed, what is the speed here to solve for that? Well, that's a pretty straightforward equation to solve. What we can do here is set 0 to the left and then go, okay, well, what is this no load speed? RA's cancel, one of the k phis cancel here, and you're left with Vs divided by k phi, and that's this guy. So this is Vs divided by k phi, right? And so what I want you to notice here is that on this side here, you do have an RA, but here you have no RA, okay? All right, so let's go to the next page and see what are the consequences of this and see how these parameters affect the curve. And we did talk about this last lecture, but let's go into it again. If your voltage supply to your motor, so you have your DC motor and you're applying a Vs to the two terminals to get it to spin. If you increase the voltage supply, you can see that Vs and Vs show up in both the Y and X intercept of this equation here. And the whole curve would shift up like so, right? These points would move to the right, these points would move up, and the whole curve would linearly just translate. And so what happens is, for the same speed, let's say you operated here, if you just increase the Vs, your ability to create torque goes up by that scaled amount, right? So now you just operate on this curve. That's kind of nice, all right? Well, what would happen if you change the resistance? Remember, this is the resistance of the coils inside the armature that spin, not the field coils, but Ra, the armature resistance. If you increase that armature resistance, what are you going to do? You're going to decrease the current, which means you're going to decrease the torque. And you can see that by just the mathematical result, right? That the Ra goes in here, is going to drop this point down. Now, like we said, there's no RA in the no load, so that point does not change. You can still get to that point, but your ability to generate torque decreases in this lower speed range. Okay, so that's the consequence of increasing the resistance. How would you physically increase the resistance? Well, let's say you had a motor where you added more turns to the or you change the gauge of the wire such that you have a thinner wire. If you had a thinner wire, you increase the resistance. And if you kept the number of turns the same, then you'd still get the same voltage, right? Or back EMF. But that would be a consequence of using thinner wire, is that your ability to generate torque goes down. Okay, what about flux? All right, so you see this phi in here, right? You see this phi and this phi. This phi is affecting both the slope and the y-intercept. So if we were to increase phi, if this phi, you can see that the phi, notice it's in the numerator for the y-intercept, but it's in the denominator for the x-intercept. So you can see as I increase phi, this point is going to slide in, but this point is going to slide up. And you can see that here. So you get this rotation. Interesting. You get this rotation. And let's think about why do you get a rotation, not just and not only just a rotation, this translation of these 2 points, whereas here you get just a rotation about that pivot point. If you have more flux or flux density, which is represented by the phi, your Bill's law equation, F equals BIL, is going to take current here and give you more force, right? So that's why you get more torque over here. But at the same time, your back EMF equation, K phi omega M, is also going to, this relationship is going to get larger. So for the same speed, you get more V induced, which, remember, the V induced, what does it do? It decreases the current, which decreases the torque. But that only happens when you have some non-zero speed. Over here is where you have that non-zero speed, not here. When you have that non-zero speed, you are getting more back EMF, less current, less torque, and that's why it's rotating this way. Over here, without the back EMF term, so no back EMF to fight your current, you get a bigger amplification of current to torque, and that's why it rotates. So you could think of adjusting the phi as a kind of a gear ratio. And let's think about how do you adjust phi? You can either do it one of two ways. Change out your permanent magnet. So you physically would you can only do this once, right? When you change the motor. So like if you have two different permanent magnet motors, one with a smaller one and one with a bigger one, you'd be here or here, right? Or if you could control the field current, because due to Ampere's law, the field current, more flux by Ampere's law, then you could also play the same game, right? You could also do it dynamically if you wanted to. But that is the consequence of changing the field current, which changes the flux. You get this kind of gear ratio, right? And what does the gear ratio do? It trades torque for speed. And that's exactly what's happening here. You're trading torque for speed, okay? So I hope this set of plots here shows you how this equation moves and changes, this line changes, and give you some intuition about the parameters that can affect the behavior of the motor. Okay, and what I also hope is that the theory, the mathematical theory, physical theory, is matching with your physical intuition about what's going on. Okay, let's keep going. So now we want to look at the power versus speed curve. So the power versus speed is different from the torque, because now on the y-axis you're going to have power. Again, I have the torque speed curve drawn. But what is power? Mechanical power is torque times angular velocity. So it's the product of these two. Whereas electrical power is current times voltage. But let's just stay in the mechanical power. Let's say I'm over here. At this point, what is the angular velocity? It's actually 0. So the power at this speed is 0. Because even though I have a large torque, something times 0 is still 0. What about over here? Same problem. I might have a lot of speed, but the torque is also 0. So again, something times 0 is still 0. So the power is 0 here, the power is 0 here. What about in the middle somewhere? Well, in the middle is actually where you get a maximum. Okay, so what we get is something like this. If I were to plot on the x-axis the same speed, right, on the x-axis, notice that I start at 0, I go to some optimal point and then come back. And all I'm doing is multiplying this speed value times torque, this speed value times torque, this speed value times torque over and over again, okay? Here's the notation. The max power developed is going to be the, I denote it by a little asterisk. It's a curved shape. It's a parabolic shape. And this here is your ideal, or what do you call it? Optimal speed that gives you the optimal power, right? Notice I have a omega m star, and notice it's half. We'll remember that it's half of the no load speed, and we'll see if we can prove that later. Okay. And then if you also follow this omega m, if we were to here, it will actually correspond to half the stall torque, right? So the optimal torque, or the torque and speed in which you get the most mechanical power, is actually right in the middle here. Interesting. Okay. Not that you can't get mechanical power here, you still get some, but you're getting your best bang for your buck right in the middle. Okay, let's keep going. So this is just, to kind of remind us of the calculus that goes in there. And what I want to see is, what is the equation that dictates finding this? Now I'm already telling you that it's about half. Half of the stall torque is the optimal torque, half no load speed is here. And the other question is, what is the power developed? Like, how would this power develop depend on like RA and phi and VS? Well, one way to do it is to take a derivative of this, set it to 0, and see what the speed is to get that 0 slope, right? This is just a basic calculus problem. And so we can take the derivative of the speed or the power with respect to speed, set it to 0, and then find and do that for this power. What's the equation for this torque? Well, we already did that. It's the k phi squared over RA and the k phi VS. Now, notice I have an omega m squared, and then I have an omega m. So it looks very similar to the torque. All I'm doing is multiplying it by speed. Okay, take the derivative of this guy with respect to speed, and what do we get? Well, this one's easy. This is just k phi VS over RA. This one's actually pretty easy too, because it's minus k phi squared over RA times 2 omega m, right? Here the omega m goes away, here the omega m stays. And that's what I get. The derivative with respect to speed is minus k phi squared over RA times 2 times the speed plus k phi over RA times VS, set it to equal to 0. Now, if I set it to equal 0, that's trying to solve for when the slope is flat, right? What's the line where the slope is flat? That's here. And I can just solve for it. Notice if I set to 0, a lot of things cancel. RAs cancel. One of these things cancel. And I can solve for this omega m, this optimal omega m, this guy here, and it's equal to VS divided by 2 k phi, and that's here. By the way, VS over k phi is the no load speed, so I hope you can see that matches our intuition that the optimal speed is half the no load speed. We could take this and plug it back into this equation to find the optimal power equation. So I'm taking 1/2 VS over k phi, plugging it back into here, and that's this one, VS over 2 k phi, and let's just see what we get. Okay, I have the squared here, so one of the k phi's canceled with this k phi, and a k phi canceled with this k phi, so I get a minus VS squared over 2 squared is 4 RA, plus VS squared over 2 RA. This cancels out to 1/4 VS squared over RA. So that means if you have a separately excited DC motor, and you know what voltage you're going to operate, and you take a measurement of the resistance, you could have an estimate of what's the maximum power it could develop given that it was operating at this speed. And you would just take, so let's say you had 100, you were going to apply 100 volts to this guy, right? And you knew the operating was like 1 ohm. You could say 100 squared divided by 4 divided by 1 would be my maximum ideal developed power I could generate. Now, of course, that doesn't account for losses because the power out is the power developed minus the rotational power. But this would be a nice equation to show you, give you a sense of how much max power you could make. Now, you have to operate at, of course, this speed. Let's see if the stall torque, or half the stall torque, would be the optimal torque. And we can do that in the next slide here. So if we know we have the optimal speed and the optimal power, we can find the optimal torque in which this occurs. So we have VS squared over 4RA divided by the VS over 2k phi. Looks like that one of the VS's here cancel, one of the 4s and the 2s cancel, and I have a k phi over RA. But if I look back at my stall torque equation, k phi VS over RA is the same thing. And look, I get T stall over 2. So the optimal power, like our intuition stated, is 1/2 T stall, or 1/2 times this guy, K phi VS over RA. Okay, so I hope all this is consistent. Really, the newness is this equation here, right? But not too bad. If I look at here, if I multiply 1/2 T stall times 1/2 no load, I get another equation for this maximum developed power as 1/4 T stall omega no load. This is just the same equation. So if they give you a spec, so they can either tell you what is the voltage you're going to operate at and what's the resistance, or they can tell you what's the stall torque and no load speed for that given voltage. What are you expecting to operate at? Either one would tell you what's the maximum power, developed ideal power you could run your motor at. Okay. Let's keep going. So let's look at a series DC motor. And like I said before in the intro, the armature and the field coils are what's put in series. And so here's a simple diagram of that. Remember, you have your armature here. If I were to get current to flow through this guy, through the Bill's law interaction, I would get torques and forces, and then the thing would spin. Now, in a series DC motor, what I'm doing is I'm taking the same voltage supply and I'm running it. So that means IF equals IA. I'm running it through the field coils, and then I'm running it through the armature. So everything is in series. That's why they call it a series motor, because the field and the armature are in series. Remember, this part spins, this part's stationary. This is replacing the permanent magnets or separately excited magnets, right? And it's using the current that is supposed to go to the armature, right? Okay. So in this case, I want to highlight again that by Ampere's law, the flux in this system here is from IF, and we know the flux, for a series motor, IF equals IA. So phi equals KFIF or KFIA. It's the same thing for a series motor. Notice this is KF. I'm just going to call it KF for like the field K. It's not the same as K as in like the back EMF K or the Bill's law K. So don't get those two confused, okay? All right, let's keep moving. Okay, what that does is it modifies our back EMF and Bill's laws equations, right? Slightly. We still have the same K phi IA, but now from Ampere's law, we are going to put a KFIA. Boom, KFIA. That's from Ampere's law. And what you see is you get two more IAs. So in a series motor, the torque is not only proportional to current, it's proportional to current squared. So that means if I double the current, I'm quadrupling the torque that I can produce. So series motors are very torquey. A lot of, powered motors, brushed power tools are series, okay? Faraday's law. Faraday's law, same equation as before. The same thing, Ampere's law applies to that phi. And so I get EA equals KKF IA omega M. So for a series motor, the back EMF is not just dependent on the speed, but it is also dependent on the current in the armature. Of course, if there's no speed, still, it doesn't matter if there's non-zero current, you still have zero back EMF. Makes sense. But if you have some non-zero back EMF and you keep that constant, you can adjust, if you have some non-zero speed, and if you adjust the armature current, you can adjust actually the back EMF that you're generating. Okay. If I were to put this and combine this with the circuit diagram, we can derive a new torque speed relationship. And so the next thing is to look at the electrical relationship inside this armature. And remember, for a separately excited, you had a separate armature circuit and a field circuit. Well, now they're all put together. And that looks like this guy. You have VS, you have the field, and then you go into the armature, RA, and of course you have your back EMF. But that's it. Just one circuit, everything in series, okay? Again, if you assume DC steady state, so I'm gonna put that in here, DC/steady state, the voltage across the inductor is 0, and you can apply a simple nodal Ohm's law across these two resistors. IA equals the node voltage at VS minus the node voltage at EA divided by RF plus RA, because these are in series. Okay, we can take these three equations just like we did for the separately excited, scrunch them together and see if we can get a new torque speed relationship, and it'll actually be a new curve. Okay, let's hold on to this. And I just want to do a quick little review because I want to give you a review of the mathematical functions that's going to give you the same thing that this will give you. So you're not like looking at this crazy equation and then seeing what's going on. It's actually going to look like this kind of fall off. In fact, it's going to be more like this one. So let me just walk you through this really quick little math review. And then when we plug all this together, I think it'll all make sense. If you have a very simple y equals 1 over x squared function where here's x and y, you can imagine you get this kind of descending curved line, right? And these asymptotes to infinity, right? Okay, so I think there should be no problem right here. If x goes to 0, y goes to infinity, right? Okay, and as x goes to infinity, y goes to 0. So the same thing. If I add a little 1 here, so 1 over 1 plus x squared, now it intersects with the value 1, because you can imagine if I put x equals 0, you get 1 over 1 squared, so that's just 1, no problem. But it still goes off to infinity. If I add some constant here, assuming that they're both positive, then now this is just a over b squared if x is 0, right? So if I put a 0, I get a over b squared, sure enough. Okay, good. And if I add one more constant in front of the c, what happens is you still have this intersection of a equal a over b squared, but now if you played with different values of c, if c was 0, you're just going to get a constant line. It is independent of x, right? It just kind of made x go away. But as you keep increasing c from 0 to 1, if c is perfectly 1, you're actually back at this scenario. If c is between 0 and 1, then you're somewhere in between. And if c is greater than 1, then now you're down here, right? Okay. The torque speed relationship for a series motor will take on this form. It'll look like an a over b plus c omega m squared. It'll look like this, okay? And that's why I bring up this mathematical review before we start crunching anything. So let me remind you of the equations. We have torque dev equals kkf ia squared. So this is a combination of Bill's law or the Lorentz force with Ampere's law. You have the back EMF equation with Ampere's law. So instead of k phi omega m, you have k and then kf ia omega m. And you have the nodal Ohm's law, ia equals vs minus e over rf plus ra. And what we can do is we can say, well, I can solve for this IA times RF plus RA that's here. And then I have this on here and I can punch in the back EMF equation. Great. I can also solve this now, one equation, solve this one equation for IA. I got IA on both sides. Now that I have this, I can plug it into here and square it. And so I get torque developed equals kkf vs squared over rf plus ra plus kkf omega m squared because of the squared. And I know you're like, oh, gross, that's a lot. But if I look at this guy, it's pretty much the same thing. And if I look at what is A, right? Well, A is kkf vs squared, good. What is this B term? B is rf plus ra, good. And what is C? C is just this kkf, no problem, right? So what we get is this, again, this equation. Remember, this is the a over b squared part. So a over b squared is just this over this squared, okay? And it goes off into infinity, and then this kkf determines how, how much it slopes down. A small number means it's gonna be flatter, a larger number means it's gonna be steeper, okay? We can see here that we have a high starting torque because it peaks up as proportional to IA squared or VS squared in this case, if you're looking at it from the perspective of voltage. No load speed. This is a very dangerous characteristic of a series motor, especially very large series motor, because when the torque is lost, right? Let's say you're driving some load and then all of a sudden the load went away. Now it's going to start speeding up like uncontrollably, and it'll break. The bearings will fail, everything will overheat. So you must have a way like to detect the RPM to be able to shut off the speed. There's poor speed regulation since the speed is proportional to the square root of the torque, right? And it's nonlinear, but it does run at near constant power, right? Because if you did like a torque times speed, torque times speed, torque times speed, you get a flatter curve, right? So as opposed to what you had before, like you had this parabola, here you're going to have, of course, 0 here and 0 way out infinity, but you're going to get something that looks like this, which is much flatter, and that's why you have this near constant power, okay? High power density, which means you can output a lot of power for a small mass. Simple to manufacture, and only one source, because you don't have to have a separately excited situation for the field and the armature. It's just one source controlling both. Okay, so this is a series DC motor. Now, the last thing I want to talk about is, well, why do they call it a universal motor? What is a universal motor? Well, a universal motor is one that operates on DC and AC. Okay, so I want to do a proof via a diagram. So if we look at this simple situation, right? So let's say we have a voltage supply and I have my motor, my field coils wound perfectly like such. I'm in this orientation. Let's just see which way the force is. Let's see if these forces are correct. If I have current running through this field coil, use my Ampere's law right-hand rule. Yep, flux density is going right to left. Okay, keep current's going to go here. Yep, flux density is going to go right to left. So this arrow is representing the flux density going right to left from the north to south. Okay. If I follow the current, it goes into the brush, into the commutator section, and let's imagine it's a coil that's going into the page, out around the back and out of the page. Yeah, and this thing's looped around, but then finally comes back out. Okay. And so if I have a current that's going into the page, so I, you can see the I there going in, and B going to the left, then force is going up on the right side here. Let's say this is the pivot axis right here. Then right here on this current that's coming up out of the page, current's coming towards me, B is going to the left, and then force is going down, boom, like this, okay? And so you can see this thing wants to rotate counterclockwise. Okay, let's say we change nothing about the physical orientation of all these things, but I flip the voltage polarity. So now instead of being a positive value, it's negative, which means the current is going to run in the opposite direction, right? Okay, let's do the same thing. So current is now running in this direction. Current's going into the page, right? And it's coming out of the page, opposite of this one. And then the current is running through the other way. So now B is going to the right. Okay, I hope you can already see it. I'm getting a double negative. I'm flipping the direction of current and the flux density, which is going to keep my force in still the same direction as the one above, still wanting it to turn counterclockwise. And we can just double check, right? If Ampere's law here says, yep, good, B is going to the right. Ampere's law over here says, yep, B is going to the right, good. And if I have my cube here, which is representing my Lorentz force, I is coming out of the page, B is going to the right this time, so F goes up, fantastic. And then what about over here? If I goes into the page, B goes to the right, yep, F goes down, again producing a counterclockwise motion. So even if I subjected a series DC motor to AC voltage in both of these cases, it would still rotate counterclockwise, okay? And that's kind of nice. So this is a series DC motor or universal motor. It'll run on DC or AC. Okay, that's all I got for this lecture. I hope you enjoyed and learned something, and hopefully it makes this stuff a little more intuitive. See you in class.